Alright, so we are going to do a review for our second exam in statistics. First thing, you got to know the vocabulary words. We've talked about this before. You've got to know them from 3, 4, and 5. You're going to find those words in your handout. And most of them, again, are listed at the beginning. You've got to know what the words are and the context of them. You also need to know, like, what these words are for all of the different charts and when you use them. Are they used for qualitative or quantitative data? That kind of thing. So these are the kinds of things you need to know. And you need to understand what those words are in context of what we're doing so that you have a better understanding of the problems. So that's the first thing you got to know. And then we're going to go over a few problems that might be similar to what you might see. They won't be the exact type of scenarios, they won't be the exact type of problems, but you need to know how to do these. All right, so our second question is, as part of a clinical trial, the drug tofacitinib, I really don't know how to say it, citrate, was administered in 5 milligram doses to 1,336 subjects as a rheumatoid arthritis treatment. Here are the numbers of adverse reactions. We had 57 subjects that had headaches, 21 had hypertension, 60 had upper respiratory tract infection, 51 had nasopharyngitis, and 53 had diarrhea. We're going to construct a frequency table and include a column for relative frequencies given as percentages. So, which side effect was most common? All right, so this is our exam 2 review. And because we're going to create a frequency chart, I need to know how many need to go in my column there. So I've got headaches, hypertension, arthritis. So that's, oh no, sorry, I skipped a line. Okay, so headaches, hypertension, upper respiratory tract infections, nasopharyngitis, and diarrhea. So we've got 5 symptoms. So we're going to have our category of symptoms. Make sure I leave enough room because we've got some big words. And then we'll have our frequency. And then we will have our relative frequency. All right, so our first symptom was headache. Our second one was hypertension. Our third one is our upper respiratory tract infection. Our next one was nasopharyngitis. And then we have diarrhea. All right. Okay, so, and then typically we're looking for the totals at the bottom, right? Because the totals will give us an idea that we're getting everybody into there. All right, so every data point is accounted for. First thing we had was 57 had headaches. Second one is 21 had hypertension. Then 60 had the upper respiratory tract infections. 51 had nasopharyngitis. And 53 had diarrhea. All right, when I add these up, I need to make sure how many of them did we have? Did it say? It doesn't say what our total is. Sometimes we get a total, right, when we've done some of these. It just said we had a total of 1,336 subjects, but it didn't say what the total is that we had. So you're going to need to make sure that you add these correctly. Use your calculator. It should be a total of 242 symptoms that occurred. So that we need because we have to be able to do the relative frequency. If you recall, the relative frequency is how this frequency relates to the total frequency. So 57 out of 242. This one will be 21 out of 242, 60 out of 242, 51 out of 242, and 53 out of 242. Now, we want to change that to be a decimal to start with. So when I put this in the calculator, I will get 0.24. This one will be 0.09, 0.25, 0.21, and 0.22. Now, if you recall, the total number of frequencies in a decimal should be equal to 1. And this one actually gets us to 1.01, which is close to 1. It doesn't have to be exactly 1. As long as it's close to it, you know that you've got your numbers correct, okay? But it actually stated that we want it given in percentages. So I need to change these two percentages by moving my decimal place 2 places or multiplying by 100. It's the same thing. So 24%, 9%, 25%, 21%, and 22%. When I sum this all up, I will get there we are. I think it's 101%. Yeah, it will because it's going over there. My notes again are a little funky. All right, so we should get to 101. I do believe. So let's add that together. So 24 plus, 24 plus 9 plus 25 plus 21 plus 22. We get 101. So different value, but just moving our decimal places as well. You just want to make sure that in the end you have 100% of your data. 99% is okay, 101%. It all depends on how they round. And these did get rounded slightly. All right. And then it asked, what side effect was the most common? Well, that's going to be one with the largest. So upper respiratory tract infection was the most common side effect. All right. So know how to do a chart and know how to pull some information out of there. All right. This was, I didn't write this one down. This is example 2. All right. So example 3. For the data set, describe the data as qualitative or quantitative and state the type of graphic that you believe would be most appropriate for displaying the data, if they were available, and explain your choice. So the data set is the colors of cars involved in fatal crashes last year. So the colors of cars, so if you recall back when we were learning about quantitative and qualitative, the colors of something are going to be a qualitative. So first of all, it's a qualitative data set. It means we're looking at the quality, the car color. Now, qualitative only has 2 that specifically go for qualitative. Usually for qualitative, you're going to use either Pareto or you're going to use a pie chart. And either one would work for this because we're talking about the quality, the color of the cars. If you wanted to see how many, like you can put it in a different order. This isn't something that's running on a number line or anything. There's no numerical other than the number, right? And the number of color, like the number of blue versus the number of red or the number of gold or number of green, those aren't necessarily a numerical situation because it's just counting how many there are, right? So a Pareto or a pie chart. Paretos are a little bit easier to see because of the way that it goes down. If you remember what a Pareto chart looks like, it's going to be like this, right? This is a Pareto versus doing something with the pie chart and the percentages. So typically these are the easier ones to read, but either answer would be okay. So Pareto or pie chart. If I was going to pick specifically one, I would probably go with Pareto, just because typically it's an easier to read and see what's going on with the data. All right. Example 4, this is where you got to know all that information about the words and the different types of graphs we have. So it says, consider the display in the figure of median salaries of males and females in recent years. What general trends does the graph convey? And then redraw the graph as a multiple line chart with 2 lines. Discuss the advantages and disadvantages of the 2 different representations of the particular data set. All right, so it is a small graph, and unfortunately I do not have that one blown up, but it's okay. So we've got male and female. The female are the shorter bars, and the male are the larger bars. And what we can do is talk about what's happening to the salaries that are happening, right? So we can see that in both cases, salaries are increasing. They both increase. They seem to be increasing at the same rate. But what we can also see, and we can see that they're steadily increasing, like they're not dipping down and then coming back up. So there's things that we can see about how it's kind of going. But we can also see that men still are typically making more money than women in this case. So they have a higher median of salaries. And part of that's because, you know, some of the men have been in their, you know, in the jobs longer because, you know, it was several years ago, but still more women were staying home way back in the day. And so men had a longer time of, you know, building up in those cases. So just in general. We also, depends on like where, if we want to look at the different types of jobs, you know, who's going more into computer programming and physics and that kind of thing. So you're looking at the median annual salaries. Not saying it's all fair. I'm just saying that's kind of, you know, part of what plays into these things. So we can kind of look at several things that we're looking in. We're just trying to pull some information off of this graph. Not trying to be political at all. All right, so, what we need to do next, we're looking at what the general trends are. So it's increasing steadily for both, and men are still, in this case, making higher median income. All right, so now it wants us to redraw the graph as a multiple line graph. So that's going to be 2 lines. Now, with this one, we're going to kind of look at, so the female salary starts at $20,000 and $30,000 is at the top right here. So it's between 20 and 30, but closer to 20 to 25,000, right? And then the male salary starts at $30,000 and it's going up to about 40,000 because those are the numbers right here. So if we want to draw the line chart, because you're like, I don't have the set of data. Well, for the first year, we would put it at the 20,000 mark, because that's 20,000, and then maybe just slightly above that, and then just slowly you're going to increase it. So if I'm going to draw a line chart, this is what it would be like, and I'm starting at 20,000. And I'm going to slowly increase it. It goes past 25,000 a little bit, but not quite up to 30. And so it's slowly increasing, and you're just kind of, because you don't have the exact value, you're just going to kind of follow the trend. And then for the males, it starts at 30 and gets up near 40. So it's slowly, steadily increasing. So if we look at these 2 graphs, you know, you got to talk about, like, what do you see the differences in them? And I realize this is not a great picture. But I think the multiple line graph makes it a little bit easier to see the trend. We can see how it bumps up just a little bit each time. We can see the bumps a little easier than looking at the tops of the bar charts. So I think that it's easier to see this. there's less clutter going on. You have two separate graphs where these kind of like are next to each other, so it's a little more clear of what's going on with them. And so maybe the data is a little bit easier to interpret. So that's all you're looking at. You just need to be able to look at the graphs and see what's going on with the data and actually give a response to what do you see, or what do you think is easier or a better way to present the material. All right. So number 5, in a survey conducted by Kelton Research, 1,004 adults were asked to identify the sounds that they find the most annoying. In response, 279 chose jackhammers, 388 chose car alarms, 128 chose barking dogs, 209 chose crying babies, and Illustrator depicts these results by using images of ears of different sizes. So for the larger one, which is going to be car alarms, they'll make a bigger ear for that. How might such a graph be misleading, and what is the general name for graphics that use the drawings of people or objects? All right, so if you recall, we looked at some similar things. We had one with the dollar in there, and then we had some with populations being shown with the different graphs. They are called pictographs. So let's go to number 5. It's called a pictograph. So with a pictograph, the problem with it is that the number of responses given in the different categories, those are all one-dimensional data, but the images of ears are going to have at least 2 dimensions. So you're going to have a width and a height, right? So it becomes like an area type of problem instead of just like a bar chart or something. And so they can be a little bit distorted. So we're going to say that this can distort the information, okay? And I realize I did not write anything down on number 4, but I think it was pretty clear on what it was. All right, so it's just going to distort it. Pictographs are not a great way to show what you're trying to show with data and things like that. All righty, number 6, describing distributions. Answer the following questions. How many modes would you expect for the distribution? And would you expect the distribution to be symmetric, left skewed, or right skewed? All right, the weights of 240 adult airline passengers consisting of 80 males and 160 males. All right, so how many modes do we expect? Well, if we're thinking about the weight of male and female, again, just like shoe size, just like height, that kind of thing. You're going to have, females and males, and you're going to have 2 modes. You'll have the average weight of, or not the average, but the most, if you're looking at modes, so the most common weight of the females and the one on the males. So I would expect it to be 2 modes, a male and a female mode, all right? And then for, as far as whether to be right skewed or left skewed, there are going to be a larger number of males because there's 160 males, right? And only 80 females. With that larger number of males, the graph is going to be more towards the right, and it's going to left skew towards the left. So this would be the majority of the 160 males. There's 80 females. Now, yes, we will have 2 modes. So it'll be a little bit bumpier. But it will skew this way because you'll have a few people that weigh a little less. You'll have some that weigh a little bit more going this way on the males. But you'll also have some that are on the lower. It's going to skew this way to the left. All right? All right, next question. We are given the following data set, It gives the driving speed of the first 7 cars to pass through a downtown intersection. We need to find the mean, the median, the range for the 2 data sets. Then we're going to give the 5-number summary and draw a box plot. Then we're going to find the standard deviation, and we're going to apply the range rule of thumb. All right, so let's go to our next page. This is example 7. So for example 7, first of all, we need to find the mean. So let me put this right here so we can see our data. So we've got to find the mean, which remember is also our x bar. We have 27 plus 31 plus 35 plus 24 plus 31 plus 26 plus 36. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Made sure I put all of my data points in there. So I have 7 terms. When I add all of that together, I get 210 divided by 7 gets me a mean of 30. So there's my mean. Now, I also needed to find the median. In order to find the median, I need to put them in numerical order. So 24 is going to be my lowest, and then 26, and 27, 31, 31, 35, and 36. 1, 2, 3, 4, 5, 6, 7. So I've got them all in order. So if I'm looking for the median, recall that the median is the middle of the row, the middle number. So 1, 2, 3, with 7 of them. If I cut that in half, it's about 3.5. So it's going to be like the 4th term. So 1, 2, 3, 4. And 1, 2, 3, 4 from in here, this will be my median, will be 31. And then I also needed to find the range. So the range will be my highest number minus my lowest number, which will get us 12. Okay, so that's part A. All right, part B says to give the 5-number summary. So 5-number summary, we've got to find the median for everything else, right? So I'm going to rewrite my list of numbers. We've got to find the median for the lower half and the median for the upper half, our min and our max. So we already know that the median is 31. And then we got to find the median of the terms below. And I've told you before that if it's an odd set, we're not going to count that one when we find our median at the bottom. So again, we're looking for the middle number, which will be 26. And that's going to be our quartile 1. And the guy at the bottom will be our minimum. And then on the upper half, with 3 digits, it's going to be the one in the center. This will be quartile 3. And this will be our max. Okay? So if we want to give the 5-number summary, then I'll have my min, my quartile 1, my median, my quartile 3, and my max. So 24, 26, 31, 35, and 36. That would be my my 5-number summary. Now, what I can do with that is create my box and whiskers. So I'm going to create the box and whiskers right over here because that's the other thing, or the box plot, which is a box and whiskers plot. So I need a number line, and I'm going from 24 up to 36. So I'm going to start at 20. And then go 25 and 30 and 35 and 40. All right, so my min is right before 25. It's at 24. My quartile 1 is at 36. The median is at 31. The quartile 3 is at 35. And the max is at 36. Now the 3 lines in the middle create the box, and then don't forget the whiskers. And don't forget to label. So this will be our min, our quartile 1, our median, our quartile 3, and our max. This is our box plot, also known as the box and whisker. Okay? All right, so it looks like we found everything for that. The next part we need to find is the standard deviation. So part C. So to find the standard deviation, the first thing we've got to know is the mean. We already have the mean found, so we can just use that mean. So I'm going to bring that on down. X bar is equal to 30. I don't have to re-find it. And if you also recall, for standard deviation, we've got to figure out how much each point in our data set deviates away from the mean. That's why it's called standard deviation, because those numbers are deviating from that mean. So we're going to make a chart. So we'll have our x values, and then we'll have the x minus x bar, and then we'll have x minus x bar squared, all right, so our x values are going to be the values that we have. It doesn't matter if you put them in order or not. It's fine. I'm going to go ahead and use this list here because it's in order. It's easy to see, but you could do them in not numerical order. It doesn't matter. So we have 24, we have 26, 31, 35, and 36. I started getting a little too close up there. All right, so our mean is 30, so 24 minus 30 will get us -6. And then 26 minus 30 will get us -4. 31 minus 30 will get us 1. 35 minus 30 will get us 5. And 36 minus 30 equals 6. So sorry. This is where our values will end up with, right? Now we got to square them. If you recall, I told you, even if it's a negative value, we're squaring the whole thing. And so it will get us a positive number every time. -4 squared will get us 16. 1 squared will get us 1. 5 squared will get us 25. And 6 squared will equal 36. And then down here, we want to find the summation of x minus x bar squared. This is the summation. That's part of our standard deviation formula. We need to sum all of these values together. So 36 plus 16 plus 1, right? Yes. Plus 25 plus 36. I'm just going to check my math over here. I want to make sure. How do we not have, oh, okay, so I just realized what I did wrong. I looked at this and I'm like, I don't have enough of the numbers. What did I do wrong here? I pulled it from this. Is this our full list? It is not. We are missing a few values here. I'm like, something's wrong here in my world. I only did the 5 here. I left out the 27 and the 31. All right, so we're going to add those on there. So be careful about that. Don't just pull from the 5 number summary. I thought, oh, this is the shortest list to look at. I need all of the data points, so don't do what I just did. All right, so we'll cross that out. We're going to add in our other 2 numbers. We are missing the 27, and we're missing a 31. So we'll just kind of ignore that part right there. So sorry. You're probably like, hey, Miss Stewart, are you giving, excuse me, so sorry. Aren't you forgetting some of the numbers? And you were correct. I'm so sorry about that. All right, so 27 minus 30 will get us negative 3, and 31 minus 30 will get us 1. All right, so negative 3 squared will get us 9, and then 1 squared again will get us 1. So I'm going to make sure I have all of my numbers and make sure it matches the math that I have written down. And it does. All right. I have all of the data points in there. So sorry. All right, so we've got the summation of x minus x bar quantity squared. Those numbers all add up to be 124. Again, as I tell you, if you were in class with me or if you've heard on other videos, I give partial credit, and this is why. It's because we even make mistakes. All right, so the standard deviation formula is S is equal to the square root of that summation of x minus x bar squared over n minus 1. That's the formula. And so we are going to use that formula to figure out what our S is. Now, I already know what this part is because that's the part right here. That's my total. So that's 124. And my n is the number of values I have, which you got to make sure you have all of your values. And I should have 7. 1, 2, 3, 4, 5, 6, 7, because that's the same number I used to find my mean, was I had 7 terms. So I'm going to divide by 7 minus 1 and make sure all of that is under your radical. This will become the square root of 124 divided by 6. And you can take that down to a decimal place if you want to. You can change it to 20.7. Or you can just leave it as 124 over 6. I'm okay with that. Just take the, you don't have to write the step is what I'm saying. But you do have to take the square root of that. And let's just verify real quick here. So if we do 124 divided by 6, notice that I've already rounded if I do that 20.7, because it's really 20.6666666, so repeating 6. So be careful about rounding too soon, but that would round to be 20.7. And if I take the second square root of 20.7, I get 4.5. If I take the second square root of 124 divided by 6, I get 4.5. So it's really close enough that it's not going to make an issue, but do be wary of rounding too soon. All right, so 4.5 will be our standard deviation. All right, was that everything on that one? It is. That was part C, finding the standard deviation for our data set. All right, now part D says apply the range rule of thumb to estimate the standard deviation of the sets. How well does the rule work in each case? And briefly discuss why it does or does not work well. Alrighty, so the range rule of thumb. So the range rule of thumb, if you remember, so I'm just going to put it here so the problem's all on one page. Part D, the range rule of thumb is going to be our range divided by 4. And that's just what you do every time. It doesn't matter how many data points you have. We already know what the range is because we already found it up here in the first part, part A. We found our range. If we didn't already know it, we'd have to go find it. That's our highest value minus our lowest value. And so we would say that this is 12 divided by 4, and this will get us 3. All right, is that close to our standard deviation? It's kind of close to it. It's just an estimation. It's not usually going to be very accurate. But we only have a small data set, right? We've only got 4 problems, or 4 numbers in here, and so because of the small data set, it's probably not going to be as accurate as if we had a bigger data set. But you at least need to be able to find what that is. All right, so a lot of things happening on one set of numbers, but it's a good thing to just not have to process too many things. All right, number 8. The table shows the batting record of two baseball players in the first half and second half of a season. Who has the higher batting average in the first half of the season, and who had the higher batting average in the second half? Who had the higher overall batting average? All right, so here is our chart. We've got the first half. These are how many hits they had, how many at-bats, and their batting average. And then second half, we have our hits, our at-bats, and our batting average. All right, so first thing they asked is who had the higher batting average in the first half of the season? All right, so this is example 8. So in the first part, if we look at the two batting averages, so we have a batting average of 0.333 and one of 0.20. Well, 0.333 is higher, so that would be Josh. So Josh had the higher batting average. In the first half of our season. And then if we look at, if we look at the second half, Josh had 0.5 and Jude had 0.467. So Josh had the highest in the second half. All right, now what we want to know is who had the higher overall batting average? Well, we're going to have to do a little bit of math here. So let's look at Josh. So Josh had 50 hits here, and he had 35 hits here. So for hits, Josh has 50 plus 35, which will equal 85 total hits. And Jude, he had 10 and 70 hits, which will get him a total of 80 hits. Now, at bats, Josh had 150 and 70. So 150 plus 70 at bats. That means how many times he was up at bat, in case you're not a baseball person. And then 50 plus 150 for Jude. So Jude had 50 plus 150 at bats in the two seasons. Now, we want to find their overall average. Oh, and I didn't do the equals, did I? All right, so this one equals 220, and this one equals 200. So sorry, those should have been in there before I put the at-bats. 150 plus 70 is 220 for our total, and 50 plus 150 is 200. So to find their average, I got to take their total of hits divided by the total at-bats. So for Josh, it will be 85 out of 220. And for Jude, it will be 80 out of 200 total. When I put this in the calculator, this one will give us, we're just going to take 85 and divide it by 220, and we get 0.386. And then for the second one, we have 80 divided by 200. This will get us 0.4, and we could add a couple more zeros on there just so that they're the same. So this is their average. So Josh had the higher batting average in both the first and then second half, but overall Jude had the higher average because 0.4 is bigger than 0.386. So Jude had the higher overall average. All right. That comes from the statistical paradox lesson that we learned. All right, on to number 9. So the figure over here to our right shows a histogram for body temperatures in Fahrenheit, in degrees Fahrenheit. 500 randomly selected adults is the distribution close to normal, and why or why not? So if you remember, a normal distribution gives you like a bell curve, right? Do we see a bell curve here? It goes up and it kind of comes down. So it looks pretty normal, so the answer will be yes. Oops, let me switch colors. So yes, one, we would expect it to be pretty normal because we're looking at body temperature, so it should be a pretty normal. And we see a bell curve. And the bell curve, remember, is something like this. I'm not great at drawing both sides evenly, but something like a bell curve. It only has one peak, because for a normal distribution, you can only have one peak. And we're saying that it's pretty symmetric, which means it kind of mirrors itself on either side. So it's a symmetric graph as well. And the other thing, if you recall, it is the body temperature is going to be a genetic item, and it's an environmental factor. Okay, and that was one of the things that they talked about, that typically when you're having a bell curve, they are affected by genetics or environmental factors. All right, I wouldn't expect you necessarily to write this, but you need to be able to tell me, well, it's got a bell curve, it's only got one peak, it's symmetric. So we're looking at it, and it is definitely a bell curve, a normal distribution. All right, number 10, consider the graph of the normal distribution in figure 512. We don't care about the number, which gives relative frequencies in a distribution of men's heights. The distribution has a mean of 69.6 inches and a standard deviation of 2.8 inches. What is being asked is, what is the total area under the curve? That's a good question. What is the total area under the curve? The total area under the curve is always equal to 1. So the total area under the curve is equal to 1. All right. Next question. The pulse rates for adult females are normally distributed with a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. Use the 68, 95, 99.7 rule to find the following values. All right, so if I'm going to be doing this problem, the first thing I want to do is I'm going to draw a number line. And in the middle of my number line, I'm going to put my mean, which is 74. And my standard deviation is 12.5. So I'm going to take 74 minus 12.5, because I need to figure out where all my numbers lie. That'll get me 61.5. Minus another 12.5 will get me 49. And then minus another 12.5 will get me 36.5. So if you recall, this is going to be our 1, our 2, our 3 standard deviations. Alrighty, so this will be 61.5, and this will be 49, and this one will be 36.5. And this will be 1, 2, and 3 standard deviations away. Now I got to figure out the other side. And for this side over here, I'm going to add. So I'll have 74 plus 12.5, and that will get us 86.5. And then I'm going to add another 12.5, and that'll get me a 99.0, right? Yeah, 80, 98, yep, 99. And then plus a 12.5 again, and that'll get us 111.5. So this again will be 1, 2, and 3 standard deviations away. So 1, 2, 3 standard deviations. We'll have 86.5, 99, and 111.5. So I want to know what my curve is. Now, if you recall that within 1 standard deviation is 68% of our data, and then within 2 standard deviations was 95% of our data, and then within 3 standard deviations was 99.7% of our data. So that's the 68, 95, 99.7 rule. All right, so our next question is, wrong side. Oh, it's up here at the top, sorry. Our next question was the percentage of pulse rates less than 74. So less than 74, if you remember, half of our data is up here or down here, and half is up there. If we're talking about 74, then it's going to be 50% because half is below and half is above. So that one is just going to be, 74 is our mean, 50% of the data will be below. The second one, part B, asks about the percentage of pulse rates between 49 and 99. So 49 to 99. Well, from 49 to 99, those are both 2 standard deviations away. So that is going to be 95% of our data. Because they're both on that line. All right, part C is the percentage of rates between 61.5 to 86.5. Well, 61.5 and 86.5, that's all the data in the 68% curve. They're both in the same increment, so this will be 68%. All right, part D asks for the percentage of pulse rates between 36.5 to 111.5. Well, 36.5 to 111.5, that's within 3 standard deviations, so that's going to be our 99.7%. And then part E wants to know the ones that are greater than 99. So we're looking for the part that's greater than 99. Well, 99 is at the 95%, right? So if it's 2 standard deviations above, 99 is, so it's in the 95%. So we're looking at what is left up here, right? So if we're looking at 95% of our data is here, we're looking for just the part that's up there. So if we take 100% and we subtract out 95%, we're left with 5% of our data. So 5% of our data, so this is our 95, 5% of our data is up and below that, right? but we only want the part up here, so we have to divide that number in half, because half of that 5% is here and half of the 5% is here above that 95%. So if I take the 5% and I divide it by 2, I get 2.5%. So 2.5% of my data is going to be above 99. So you need to understand this rule, and you need to be able to pull these apart. You had an activity on this, you had homework, and we did an extensive example on this in the lesson. So make sure you know how to do these. All right, number 12 is our last problem. The heights of adult American males are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. The U.S. Marine Corps requires that males have heights between 64 and 78 inches. Convert 64 inches and 78 inches to a z-score to find the corresponding percentage. All right, so for number 12, we are looking at finding the z-score. If you recall, z is equal to your x value minus mu over sigma, which will be equal to the data value minus the mean over the standard deviation. All right, so that's our formula. Now we got to go figure out what all of those are. So we have a mean of 69. All right, so our mean, let me put this in a different color. Our mean equals 69. Our standard deviation is 2.8. So the standard deviation equals 2.8. And our x values, we actually have two of those. We have convert 64 and convert 78. So our x value, or our data value, is going to be equal to 64, and then we have an x equal to 78. All right, so let's go do the formula to find the first one. So z will be equal to 64 minus our mean of 69 over a standard deviation of 2.8. This will get us negative 5 divided by 2.8, which will get us negative 1.79. And we'll go find the percentage here in a minute. Let's do our other z-score. So our other z-score is going to be 78 minus our mean of 69 divided by the standard deviation of 2.8. This will get us a difference of 9 divided by 2.8, which will get us 3.21. Now, if you recall, we need to use the z-score table to find the percentage. So, we're going to use the z-score for 1.79 to find our 1.7, negative 1.7. So we'll go on, I just have part of the z-score on here. So we'll go down to negative 1.7, and then we go over to 0.09 because it's the second decimal is on this part here. And we pull together, coming across and down, and we end up at 0.0367. So this will become our 0.0367, which then when we change it to a percentage, it'll be 3.67%. Okay? And then the next one is 3.21, so we're going to come down to 3.2 and over to the 0.01 and come down where they meet, and we get a 0.9993 right there. So this one becomes 0.9993. And so when we change this, it'll become 99.93%. Okay? So we found the z-score, and then we found the corresponding percentage. Now, a commonly asked question by students is, on the test, do we have to memorize? Memorize? No. You need to understand how to do things. The formulas will all be provided, and also if you need the z-score table, it will be there. You don't need to memorize it. I would never memorize this. So the information that you need as far as formulas and the z-score table will be available to you if it's needed. You have to understand how to do all the problems, and you also need to understand your vocabulary. Work out your review repeatedly to make sure you can actually do it without looking at your notes, and you should be okay on the exam.